Now that we have an introduction to what machine learning is, and we've oriented ourselves to the R programming workspace where we'll be working on the applications, it's time to move into the meat of the course, and that is the mathematics. We'll begin here with linear algebra, specifically in this lesson, scalars, vectors, and matrices. Now, this lesson will be very introductory in terms of the content. So if you're familiar with some linear algebra, it'll be a quick review for you. But I don't want to understate the importance here of this lesson and the next couple, because all of the mathematics that we get into, even the deep mathematics involved in machine learning, will be built on the foundation of scalars, vectors, and matrices. In other words, these foundational components serve as the building blocks for all of the deeper mathematics that we'll touch on. So it'll be very important that we are on the same page in terms of the terminology and the notation and the rules. So for this lesson, in terms of an outline, we'll start with some basic definitions, we'll move into a few examples, and then we'll discuss a final concept which has to do with vectors in space. So some definitions. First of all, a scalar is simply a constant. Just think of any number, 3, 8, -5, 1/2, 7/10, it doesn't matter. Any number, it's just a scalar, it's just a quantity. Then we get into collections of numbers, and the first one we want to discuss is a vector. So a vector is simply a single row or column of numbers. It's a single array that's a collection of numbers. So we have a couple of examples there. We could have one row that's -1, 2, and 5, for example, or we could think of that same collection as a column of -1, 2, and 5. You could have any number of entries that you want there. It's just a single row or a single column. Then we get into full rectangles, and those are where we get into matrices, a rectangular collection of numbers, or really any entry. It doesn't have to be numbers, but most of the time when we're working with them, it will be. So here we see the first example has, we have 3 rows and 3 columns, and then this one we have 3 rows and 5 columns, and so we have 2 rectangular collections of numbers, and that's what we mean whenever we say matrix. So a scalar for our purposes is simply a number. A vector is a collection of numbers, that's a single row or a single column, and then a matrix is a full rectangular collection of numbers. Now, dimensions of a matrix will be very important. The dimensions, I touched on it just a minute ago without the formal definition. It refers to the number of rows and columns in a matrix. An R by C matrix has R rows and C columns. And then we'll use the notation here, M sub ij, where M generally represents the name of the matrix. So this would be some matrix named M. The mijth element is at row I and column j. So row I and column j. It's an important convention in matrix algebra that when we're talking about the dimensions, the first number represents rows and the second number represents columns. That's really just a standard convention to help everybody stay on the same page and everybody stay organized. We know if we're talking about an R by C matrix, everyone will know that you mean R rows and C columns. And so it could be a 2 by 3 or a 3 by 5 or a 1 by 6 or whatever. So here's an example of a matrix named M. And you can see the entries run from M11 in the top left corner all the way to the bottom right corner, MRC. So let's take a few seconds here just to orient ourselves to the notation and particularly the subscripts. So we have here R rows. We see then that our first index on the subscript counts the rows. And so we go from M11, which is element M in the first row and the first column. And then we come down to M21, which is the element in the second row and the first column. And that proceeds all the way down to the last row where we have the element in the rth row and the first column. So we have rows 1 through R in column 1. Then we move to column 2 and we see the same sort of indexing. Our first index runs 1, 2, all the way to R, and the second index represents the column number, so it's all 2 for the second column. And then this proceeds all the way over to the last column. Again, on our first index, we see 1, 2, all the way to R, representing the rows, and then this is the cth column. So first row, cth column, second row, cth column, and then the rth row, cth column in the bottom right-hand corner. So remember, matrices are always represented by their dimensions, rows, and then number of columns. So here's a quick example for you. What are the dimensions of each matrix? Go ahead and pause the video here for a few seconds. Determine what the dimensions of each matrix are, and then push play again and I'll give you the answers. Okay, let's take a look at the answers. What are the dimensions of each matrix? Well, matrix A is a 2 by 3. We can see here that it has 2 rows and 3 columns. Matrix B is a 2 by 2. It has 2 rows and 3 columns. And then matrix C is a 1 by 3. There's just 1 row, but we do have 3 columns. So a 2 by 3, a 2 by 2, and a 1 by 3. Rows, then columns. Here's another example. Find the listed element of each matrix. Go ahead and pause the video again, and then come back whenever you think you have an answer, and we'll discuss it together. Okay, let's take a look. What is the listed element in each matrix? Well, we have element A23 in matrix A is 1.6. Recall from the previous slide, a couple slides ago, we had the indexes represent row and then column. So this is the element in matrix A in the second row in the third column. So we come to the second row, we go to the third column, it's 1.6. So A23 is 1.6. In matrix B, we're looking for the element in the second row in the first column. So we go to the second row, first column, it's e to the 2x. And then in matrix C, we're looking for the element in the first row. In the second column, there is only 1 row, so we go to the second column, and it's C sub 2. C sub 2. So that just orients you to the elements and the entries in a matrix according to their rows and dimensions and their subscripts. Now, here's another thought on dimensions. And you actually might have thought of this on the last example when we got to matrix C that had only 1 row. Vectors are always represented as a single row or column, as we defined early in the lecture. This means that they are a subset of matrices, because we said matrices simply have R rows and C columns. Well, if one of those is a 1, either 1 row or 1 column, then we simply have a vector. So vectors are a subset of matrices. In other words, vectors are simply matrices that have the dimensions of either 1 by C or R by 1. 1 by C would mean there's 1 row and some number of columns. That would be a row vector, like we saw with C in the last example. Or we have R rows and 1 column. So it would be a column vector. And scalars are 1 by 1, really 1 row and 1 column. There's only 1 entry to speak of. Now that does present a little bit of a problem to think of it that way whenever we get into some of our matrix operations, but for all intents and purposes, scalars are essentially a 1 by 1. Here we can see it organized a little bit for us. Matrices, again, are the superset. So as we're progressing through this lesson, scalars, vectors, and matrices, really we're talking about one superset, and that is matrices. They can have any number of R rows and C columns, provided that R and C are positive integers. Then the next subset would be vectors, where we have either 1 row or 1 column, but there's no restriction then on the other dimension. So if we have 1 row, we can have any number of columns, or if we have 1 column, we can have any number of rows, and it's still a vector. And then scalars are 1 by 1. So again, matrices are the superset, first subset is vectors, and the most restrictive set are scalars. Now let's briefly discuss vectors in space. So vectors are also used to represent locations in space, particularly on a graph or a coordinate grid. And each entry, whenever we do this, represents a dimension. So 1, 2, or 3 really are the only ones where we can actively visualize this. If we get into a vector with, say, 4, 5, 6, 7 entries, well, we can't visualize things in 5 dimensions, for example. But in 1, 2, or 3, we can see it and we can get an intuitive sense of what's going on. And so we discuss these in terms of n space. So if a vector has 1 dimension, like this one, we look at it in 1 space or in 1 dimension. The vector u has only 1 entry, it's -3. We can see it on a single axis or a single dimension. It's simply a point at -3. Now you might be familiar from your algebra course with a two-dimensional representation. So this would be two space. Vector v has two elements, 2 and 4. From your algebra class, you'd be used to seeing those written in a set of parentheses with a comma between them. We call them ordered pairs in a more of an algebra setting. And the first one would represent your quote-unquote x coordinate, and the second one would be your y coordinate, or your horizontal coordinate followed by your vertical coordinate. So the vector 2, 4 can be represented at point 2 comma 4, so to speak. And then the vector actually runs from 0, 0 to 2, 4. So vectors are arrows whenever we get beyond a single dimension. So once we get to 2 space, 3 space, 4 space, and so on, they're really n-dimensional vectors. And now we can see it in 3 space as well. If we have vector w that is entries 2, 3, and 4, then we can think of these as our x, y, and z coordinates is the standard notation. So we have 3 axes here, starting at 0, 0, 0. We move along the x-axis, then the y, and then up in the third dimension for the z coordinate. So at this point we can see it sort of traced out for us. We would move 2 along the x-axis, followed by 3 along the y-axis, and then up 4 to get to point 2, 3, 4. That would be the red point, and then the three-dimensional vector runs from 0, 0, 0 up to our ending point. And so we can see whether it's 1 space, 2 space, or 3 space, we have a physical representation for the vector in space. And so that really is kind of just beginning to scratch the surface. When we get into section 3 of the course and discuss vector calculus, we'll get a lot more into the mathematics of vectors and vector spaces, and that is really where we'll begin to get into a lot of the deep vector mathematics at that point. But this gives you a little bit of a preview and a bit of an intuition. Next, we'll switch over in the next video over to the R workspace, and we'll do some of this programmatically. See you there.